Okay. Okay, so welcome everyone. It is great pleasure to have Mario Beraha from the Polytechnic University of Milan for the first BNP webinar of this academic year. It's been a while since our last one. He will present one of his recent works on the Bayesian feature allocation models. Let's welcome Mario, and Mario, floor is yours.
Thank you. So let me just share my screen and start the slides. And you should be seeing my slides. Okay, so today I will be talking about what we call the extended feature allocations and some related problems. So a feature allocation is a stochastic model that that we use when we have data recording the patterns of presence or absence of certain features. So this means that each observation can be described by a set of the features that it displays, here called x tilde I from 1 to ni, where ni is the number of features of observation I. And if the space where these x tildes live is not too wild, then we can enumerate them and represent each observation zi as a counting measure supported over all the possible features, where these binary indicator variables are equal to 1 if observation I displays feature j and 0 otherwise. And this can also be visually encoded in a binary matrix where columns correspond to the different features and rows correspond to the different observation. And here I colored each cell in blue if a given observation displays a certain feature. So before going into the talk, let me just give you some ideas of where these models can be applied. So one application is in text mining. And in text mining, features are different words and observations are different documents. And we represent each document as the set of words it contains and in doing so, we disregard both the ordering of the words and how many times each word appears. But nevertheless, this is a rather common assumption in topic modeling and text classifications, for instance. Another completely different application for feature allocations is in genomic studies, where the features are different genomic variants, which means basically that we have a template DNA of the human, so a template sequence of the human genome, and then we sequence the DNA of different people, and we look if these match, or there are portions of the genome in which these two DNAs do not match. In case they do not match, we call the portion where this doesn't match a genomic variant. And we represent each observation, that is each patient, by the set of genomic variants they display. So while these two applications are completely different, there are something in common between them. And the thing is that the feature, the numerical value associated to the labels xj, to the features xj, is basically meaningless. And the only important thing is that these xj's are different from one another. And in these cases, so where we can ignore the values of the xj's, the focus is mainly on the feature allocation, that is the distribution of this binary matrix up to a permutation of the columns. And the inferential goals are mostly concerned about prediction. For instance, if I have a sample of documents, I want to predict how many new words will I discover if I look at the next 100 documents. That is, words that did not appear in the original text, but will be discovered in the next 100 documents. And in the context of genomic studies, the same question basically is to estimate how many new genomic variants will I discover if I were to go on and sequence the DNA of an additional sample of patients or individuals. By contrast, there are some settings in which feature labels are important, and estimating the features is maybe the goal of the inference. One of such examples is in image segmentation, where observations are images. Here I'm displaying a potential sample, potential data set of 4 images. And we recognize that observation 1, 2, and 4 display this feature that is a white cross in the top left corner, while observation 2, 3, and 4 display this other feature that is this staircase in the bottom left corner. And in this case, we do not directly observe the features, but rather we assume that they are present at a latent level. And the focus of the inference is exactly estimating these features and referring each image to the feature it displays. Another setting where feature labels are important is the following, and will also be the object of a numerical illustration that I will present at the end of the talk. And in this case, we have that feature labels, the XJs, are the position of trees inside of a forest. And we have observations that mark the position of only a subset of the trees in the forest, because they are generated by human surveyors that are people that go in the forest, and with a GPS, they mark the position of the trees they see. And of course, being time limited and being human, they will miss some trees. And in this context, we can ask ourselves, how many trees are there in the forest? This is a classical question that has been already asked 50 years ago with this kind of data. But we can also ask ourselves where are the missing trees that we did not observe? And so the key difference between extended and standard feature models is that in extended features, each feature has a specific interpretation. And then we argue that it is important to model the interaction between different features. For instance, if we were to assume that 3 locations are i.i.d, this would be kind of unrealistic, because in reality, trees repel each other, especially very big trees. It's very hard to see 2 extremely large trees near each other. And if we were to predict where were the missing trees, if we were to assume that positions are i.i.d, then we could not ever estimate where are the missing trees. And similarly, if we were to assume in the image segmentation task that features are i.i.d, this might produce redundant features. So we would overestimate the features, which makes posterior interpretability harder. And you can think of this as basically the same issues that happens in model-based clustering, which led to the introduction and study of repulsive mixture models for Bayesian model-based clustering. And so with this notation, with this framework set up, I can now say what I will be talking about for the rest of the talk. So in the first part of the talk, I will be talking about models for feature allocations. Up to now, I've been talking about data and inferential goals, and in particular, Bayesian nonparametric models, focusing in particular on what happens when you assume completely random measure priors. Then I will be talking about a specific application of trait allocation of trait models, of feature allocation models for a problem of activity prediction in online A/B testing. And then I will move on to a more mathematical part of the talk, which will try to understand which priors lead to simple predictive distribution, and use this analysis to analyze the forest data that I just mentioned. So getting on with the talk, the first and probably most famous model for feature allocations is the Indian buffet process. So this is actually a metaphor for a stochastic process that defines a distribution over sparse binary matrices, where customers enter in sequentially, one by one, in a restaurant that serves an Indian buffet with infinitely many dishes. And so the metaphor goes as follows. The first customer enters in the restaurant and draws a Poisson random variable, say K1, which is Poisson with parameter theta. Suppose that K1 is equal to 3, then customer number 1 selects the first 3 dishes. Then, after n customers have entered, customer n plus 1 goes through the buffet and selects each one of the dishes that were previously chosen, and there were kn dishes that were previously chosen. In this example, we have that n is equal to 3 and kn is equal to 5. And they choose each one of the previously chosen dishes with a probability that is proportional to their popularity. That is, how many times dish J was previously chosen. And after reaching the kth station of the buffet, they draw another Poisson random variable, k prime n plus 1, which is again Poisson distributed with a parameter that is theta rescaled by n plus 1, and selects those many new dishes. In this metaphor, there is no mention to the feature labels, which are then attached to the column of this binary matrix by sampling them i.i.d from a diffuse probability measure G0. And a key contribution that linked Bayesian nonparametric models with the Indian buffet process was due to Thibault and Jordan, that proved basically that a sample from an Indian buffet process has the same distribution as a sample from this Bayesian model, where we have a random object here that is a completely random measure, and in particular, it is distributed as a beta process. So mu here collects all the possible feature values xj and assigns to each feature its popularity, if you will, sj, that is a score in between 0 and 1. And conditionally to mu, observations are i.i.d from a Bernoulli process, which means that zi is a counting measure supported over all possible features. And these binary indicator variables are Bernoulli with parameter sj, i.i.d across individuals, and independently across features. Having established this clear connection between feature models and Bayesian nonparametric models, then it's clear that one can generalize the Indian buffet process by changing either the likelihood part or the prior part. In particular, if we choose carefully the Levy measure of this completely random measure, then we can have models that exhibit power laws in both the number of distinct features that are chosen and the number of features that select, the number of customers that select each dish. But we can also generalize the model by assuming that the Bij's are not binary variables, but are integer or even real valued. And we can consider more complex dependencies, such as to deal with partially exchangeable data by exploiting the rich literature on hierarchical complete random measures. So as I said in the beginning of the talk, one of the goals when the feature labels are not relevant, and in this case, I would argue that we are assuming that feature labels are not relevant since we are basically sampling them i.i.d from a diffuse probability measure. The goals are about extrapolation or prediction. And in the original Indian buffet process, we have that the extrapolation procedure, that is, how many new features are selected by customer n plus 1, this random variable is a Poisson with parameter that depends only on the sample size. So if we go back to one of the applications I was mentioning on, this means that if we assume the Indian buffet process for the genomic variant study, this means that the probability that I will discover new genomic variants in the future depends only on the sample size, regardless of basically whatever I have seen in the samples. And this is a rather poor predictive structures and constitutes a serious limitation of the Indian buffet process in such prediction tasks. Of course, we can ask ourselves if this is inherent to the Indian buffet process or pertains also to other models. And in this paper by James in 2017, it is clearly shown that this predictive structure is not specific to the Indian buffet process, but belongs to all priors based on completely random measures, where k prime n plus 1 is a Poisson random variable with a parameter that depends exclusively on the sample size. And so this behavior is inherited by the Poisson process construction of complete random measure, and morally can be traced back to the fact that there is too much independence in the joint distribution of the jumps of this measure. And if we want to obtain richer predictions, then we need to step out of the class of completely random measure and define other distribution for random measures. But of course, there is a trade-off to balance here, because the more independence we put in the prior, the more it is likely that we will have tractable posterior expression, which result in a closed form and easily computable estimator. The more instead structure we put in the prior, the more dependence we put, the more it is likely that posterior inference becomes intractable, and we will need to simulate using Markov chain Monte Carlo, which might preclude some large-scale application. So in this context, Kamerlenghi and co-authors in 2024 proposed to use scale processes as priors, which is another class of priors from complete random measure, and can be roughly defined as follows. So you start from a complete random measure, a homogeneous one, and you take out the largest jump of this random measure. And conditionally to saying delta 1 equal to zeta, you divide all the remaining jumps by the largest one, after which you can perform a change of measure for delta 1 to obtain further flexibility. So this may sound rather obscure, but it is clear that by doing so, scale processes introduce a lot of dependence on the joint distribution of the jumps, which in turn we will see that leads to richer predictive distribution. So after this very broad overview of Bayesian nonparametric feature allocation, I want to move on to talking about a specific application of scale process priors for user activity prediction. And this is based on joint work with Lorenzo Masoero and Thomas Richardson at Amazon and Stefano Favaro at University of Torino. So basically our setup is the following. We have data from an e-commerce website where for each user, we record some daily activity, meaning we know if a user is active or not active on a given day, where activity could mean like clicked on a web page, logged on some cloud computing platform, or purchased a product, or so on and so forth. And in these situations, what we want to do is to estimate or predict how many new customers will trigger or be active at least once in an additional period of time. And this fits into a much broader goal, that is to predict the power of an A/B test for the effectiveness of a treatment, where treatment here could mean like changing the font or the color of a web page, changing the login interface, or things like that. And the only constraint that we have is that we have huge data sets. That is, for each experiment, we have millions of customers that are active any given day. And so we cannot afford to run MCMC on these large-scale applications, and we need tractable models to perform rather fast inference. And so our idea was to use feature modeling in the following sense. So the first thing is that we identify features with users. And so here, the columns of this binary matrix represent the IDs of the users, and observations are the days of the A/B test. And so we have that for each day, we mark which users are active. And then our measure mu collects all the possible label or user labels and assigns to each user their propensity to engage, where this SJ, if it's closer to 1, it means that a given user is likely to be active every day, while if it's closer to 0, then it means that it's a user that is seldomly active. And conditionally to mu, we can model the full binary matrix, in which case we refer to what we call a Bernoulli model. That is the typical generalization of the Indian buffet process, where Zi given mu are i.i.d from a Bernoulli process with parameter mu. But the potential pitfall of this kind of model is that there is some degree of model misspecification that we need to be aware of. In particular, if being active means going on a website and buying something, then if you do it on one day, it is very unlikely that you will do it again the next day. So the fact that we assume that days of the experiments are conditionally i.i.d might not hold. And so to mitigate this, we also investigated another model, which models only the first triggering times of each user. So Here, yj is the first day in which user xj is active, and it's 0 if user xj is never active in the first observation period. And we assume that yj given mu follows basically a truncated geometric distribution, which means that it is just a geometric distribution of 1 to n, where n is the number of days. And we put to 0 all the values of yj that are greater than n, meaning that we don't observe that specific user. Of course, the potential pitfall here is that we are losing a lot of information. If the assumptions that the experiment days are conditional i.i.d. Holds, then here we are throwing away a lot of information. And in some cases, we don't have only information about if a user is active or not, but we can also quantify the activity of a user in terms of how many times they are active that day. That is, how many times they click on a web page, how many times they perform a login, and so on and so forth. And we can accommodate this by generalizing our models and saying that xj is associated with a certain activity on day I, which we model as an independent negative binomial distributions. So this was about 3 different likelihoods that are accumulated by the choice of the same prior for mu that is distributed as a stable beta scale process, which is a special class of scale process built from a stable random measure, which can be basically expressed as follows. So we have that mu given the tilted version of the largest jump is a completely random measure with a certain Levy intensity, and the tilted version of the largest jump to the power minus alpha follows a gamma distribution. And then given observation, in all our models, the posterior of mu can be decomposed as the sum of 2 parts, where the first part is supported only on previously seen users, and in particular, these S stars here are independent beta random variables, while mu prime is supported only on the unseen users so far, and is still a stable beta scale process. So this allows us to have a closed form expression for posterior and marginal distribution. In particular, we use empirical Bayes to fit the hyperparameters in the model by maximizing the marginal log likelihood. And this closed form expression for the posterior, in turn, allows us to get a closed form expression for the number of users that will be active at least once in the following n star days. We call it un n star. That is the number of users that were not active in the first days, but will be active at least once in the following n star days. And this follows a negative binomial distribution where the second parameter is a function of the sample size, the number of experiment days, and the number of follow-up observation days. And the first parameter depends on the number of distinct features or users that were active. And so in this case, we have that predictions depend both on the sample size and the number of distinct features. And so we have enriched the predictive distribution compared to what happens if we were to assume a complete random measure prior. Of course, we performed extensive numerical simulations to validate our model. And in particular, here I'm reporting the result from a meta-analysis of 210 A/B tests, where we compare a total of 9 models on the unseen user prediction task. So basically, we have data for the first 7 days of this A/B test, and we want to extrapolate and estimate how many users will be active at the end of the 4th week. And I won't go into the details of all the competitor models, but basically here IBP is a slight modification of the Indian buffet process based on the 3-parameter beta process originally proposed by Tay and Gorur, while HBG is another Bayesian model that is the one currently employed by this company. BM is our Bernoulli model that models the full binary matrix, while GM is the geometric model still developed by us that models only the first triggering time. And so to compare the different model, we resort to this robust comparison metric that is based on model ranking. So for each experiment, we assign to each of the competitor rank, where rank number 1 means that it gives the best prediction, and rank number 9 means that it gives the worst prediction. And here in this plot on the top left, I report how many times out of the 210 experiments each model gives the best prediction, so it's ranked number 1. And we can see that the geometric model is the one that clearly outperforms all the other ones by ranking first 25% of the time. And here I report the number of times that each model is either first or second in the rank. And the geometric model does so more than 50%. And so I think that this is a very nice example of the possibilities of Bayesian nonparametric models, because we had to digest a lot of math in order to arrive to this kind of estimators. But in the end, both the estimators are extremely easy to compute. It's just computing a negative binomial distribution with some parameters that are nothing crazy to compute. And it also shows that our Bayesian nonparametric approach, at least in these 210 experiments, clearly outperforms all the possible competitors. So I think that now would be, I don't know if it's okay, but if there are questions on this first part of the talk, I can take some of these now and then move to the second part of the talk, which is much more mathematical. Okay, so if there are no questions, then let me just move on to the second part of the talk, where I will be talking about extended feature models and prediction. In particular, what we want to do is to develop sufficientness postulate for feature models. So to understand what a sufficientness postulate is, consider a Bayesian model for some observation Zi, which depend on some random the model depends on some random parameter theta, which is given a prior pi. What we want to do is to characterize a specific prior distribution or a family of prior distribution based on some characteristic or properties of the predictive distribution induced on observation n+1. Why is it important? Well, it gives, apart from being mathematically an interesting problem, it also gives a principled way on how to choose a prior distribution, because it is often easier to reason about predictions than it is to reason about priors, especially in nonparametric models. And what are these specific characteristics of the prediction distribution that I will be talking? They will be related to the distribution of the number of new features displayed by observation n+1. So in particular, we have seen that for completely random measure, the law of k prime n+1 depends only on the sample size. While in the stable beta scale process, this depends also on the number of distinct features displayed on the sample. And so what we want to do is to characterize which prior leads to this kind of predictive behaviors. So predictive characterization in the feature sampling or feature allocation setting are not widely studied, but there is a rich literature in the species sampling setting. And formally, we can consider a species sampling model as a subclass of a feature allocation model, because in a species sampling model, we have that observation display only one feature, that is its species. But mathematically, these are very, very different objects. In particular, in a species sampling model, we have that observation are i.i.d. from a random probability measure P, such that the atoms of P are i.i.d. from a diffuse probability measure, and the weights of P live in a suitable probability simplex. And so in this setting, sufficientness postulates have been developed starting from the 1920s. In particular, Johnson considered the case of a fixed and known number of species and characterized the symmetric Dirichlet distribution as the only distribution on the simplex for which the probability that a new observation belongs to species J given observations depends on the sample size and the number of observation of species J in the sample, and nothing else. If we want to generalize this treatment to infinite species or nonparametric models, then we need somehow to account for the possibility that a new observation, observation n+1, displays a feature that we have not already seen in the simplex, in the sample, and we didn't have any information that such species existed yet. And I will indicate with this case with Zn+1 is new. And in this context, Regazzini and later Lowe characterized the Dirichlet process as the only species sampling prior for which the probability of reobserving an already seen species, an old species, is as before, while the probability of seeing something new depends on the observed sample only through the sample size. Later on, Zabel characterized the Pitt-Major process for which the probability of seeing something old is as before, while the probability of seeing something new depends on the sample size and the number of distinct species displayed in the sample. And in recent years, Bacallado and co-authors characterized Gibbs-type priors as the only family or class of species sampling priors, such that the probability of seeing a new species is as before, so depends on the number of on the sample size and the number of distinct species, but the probability of seeing something old depends also on the number of distinct species. And so to generalize this treatment to feature setting, we assume the usual model where observations are conditionally from a Bernoulli product model. And the prior for mu is Q, which might belong to a suitable family of prior, such as complete random measures, scale processes, or might be even more general. We denote the sample by Z1, Zn. The sample displays Kn unique features with labels x star 1, x star Kn. And K prime n+1 is the number of new features displayed by observation n+1. And so in this context, the only work about predictive characterization or sufficientness postulate in the feature setting is due to Camerlenghi and Favaro, that characterize those scale processes that lead simple predictive rules for K prime n+1. In particular, they show that K prime n+1 depends only on the sample size and the number of features if and only if mu is a scale process built from a stable complete random measure. And in particular, in the example that I showed you before in activity prediction, we were considering a specific example of this class of priors. And in fact, our predictions were depending on both the sample size and the number of features. The weakness of these kind of characterizations is that they hold true only in the class of scale processes. While it is general to ask ourselves if this characterization holds true in a much broader sense. So it is only scale processes built from stable complete random measure that yield these predictive structures, or we could choose other prior and have analogous predictive structures. And to answer this question, we set ourselves in the extended feature framework, where the likelihood is just as before. And for the prior, we simply assume that mu is almost surely discrete random measure with jumps in between 0 and 1. So this means that mu can be written as a functional of a point process psi, which collects the feature label xj and the jumps sj. And of course, these two objects are in one-to-one correspondence, and it's likely that I will mix between the two when presenting our results. What is important here is that we don't assume anything on this prior Q, which means that there could be any sort of dependence between these random variables. In particular, the xj's could be dependent between one another. The jumps sj could be strongly dependent or independent. And there could be also dependence across the jumps and the feature labels. So basically, this is the largest class of priors one can think of because we have not specified any prior for this. We are just saying that this is an almost surely discrete random measure. With the only assumptions that these xj's are pairwise distinct almost surely, then we can write the predictive distribution as follows. So the predictive distribution for Zn+1 decomposes as the sum of two terms, where the term of the left is supported on the previously seen feature. So with positive probability in observation n+1, I can reobserve each one of the previously seen feature. And the second term is supported on unseen features. So observation n+1, of course, can display new features. So with this notation, Camerlenghi and Favaro perform characterization based on the total mass of Z prime n+1, while I will prove characterization based on the whole distribution of Z prime n+1. That is, how many features and also their labels. This is not a big deal, because if we restrict our attention just to the class of priors for which the feature labels are i.i.d, then the number of features and the distribution of Z prime n+1 are in one-to-one correspondence. So we are not losing anything in working in this more general setting. And so we can state our characterizations results. And in particular, we were able to show that the law of Z prime n+1 depends on the observed sample solely through the sample size, if and only if psi is a Poisson process, that is, mu is a complete random measure. And this covers both the case of a finite and infinite number of features. So if the number of features is finite, let's call it capital M, then capital M must necessarily be random and Poisson distributed. And given M, the points in psi must be i.i.d from a measure on the space where the feature lives times 0, 1, that we call omega. While if instead the number of features is infinite, we recover the standard construction of complete random measures that we typically employ in Bayesian nonparametric. Instead, if we look at those predictions that depend on the sample size and the number of unique features, then this is unique to those measures built from a mixed Poisson or mixed binomial process. So in the case of a mixed binomial process, we have a finite number of features where Km follows a distribution Pm, which must not be Poisson, otherwise we fall back to the Poisson process case. But other than that, Pm could be anything, could be also a point mass at a specific value, in which case we have a fixed and known number of features. And conditionally to M, the points in psi are i.i.d from a measure omega on the space where the x lives times 0, 1. While if instead we have an infinite number of features, then we are dealing with what we call mixed Poisson processes, which means that there exists a random variable theta on R plus distributed as pi theta, such that mu given theta is a complete random measure with a Levy intensity that is nu, which is a proper Levy intensity measure, rescaled by the scalar theta. In particular, this shows that prediction depending on n and kn pertain to a much broader class than scale processes built from stable random measure, and actually do not even identify a unique class of processes, but we need to look, so they pertain to a lot of prior distribution, the ones built from mixed Poisson and mixed binomial processes. So many prior distribution lead to this kind of predictive structures. So I won't go into the details of the proof, of course, but let me just say that our proofs are analytical, in the sense that the building block of our proof is a general expression for the posterior distribution of psi, or mu. As I said, they are interchangeable. And mu given the observation is written as the sum of two terms, where the first term is supported on the previously seen features, and mu prime is supported on the unseen features. In particular, the law of mu prime uniquely determines the law of Z prime n+1, that is the new features displayed by the observation n+1. And while the law of mu prime is a rather complex object, so in our expression, we say that we have a closed form expression because we know it's Laplace functional. So in theory, we know everything about mu prime, but it is not a very tractable object. We know that it depends on the sample size we depend on the sample through the sample size and the reduced Palm kernel of psi, that I will explain, at least give an intuition of what it is in a second, which carries information, this reduced Palm kernel, about the unique features, so the labels x star 1, x star kn, their cardinality, and how many times each feature appears. So this depends on the whole sample in general. So the reduced Palm kernel of a generic point process phi at a k tuple of points y star, y1 to yk, can be interpreted as the conditional law of phi, given that we know the location of k of its atoms. And so our characterization are basically based on the following characterization for point processes. So we moved from characterization of predictive law to characterization based on Palm kernels. And in particular, we show that the reduced Palm kernel of a point process is independent on the conditioning point, if and only if this point process is a Poisson process, or depends on the conditioning points only through their cardinality, but not their location, if and only if this point process is a mixed Poisson or mixed binomial process. And this basically is how we were able to get our characterizations. So moving on to the last part of the talk in a few minutes I have left. As I said, since our proofs are analytical, a byproduct of our study were that we were deriving general, posterior, and predictive distribution. And I think I've already mentioned that these are usually complex objects, but the more independence we put in the prior, the more these objects simplify. And in particular, we were able to find a particularly tractable case when psi is an independently marked determinantal point process, which means basically that the feature label xj are jointly distributed as a determinantal point process with a given covariance C, while the sj's are i.i.d beta random variables. So in this case, in the posterior expression, the S stars are independent beta random variables, while mu prime is independent of the S stars and is another independently marked point process with S prime j's i.i.d beta random variable and support points that together form a point process with a tractable law because we have its density in a closed form with respect to another determinantal point process. And in particular, we can show that the law of z prime n plus 1 depends on the sample size, on the number of distinct features and their locations, but not on how many times each feature appears. And so with this model, we analyzed the forest data that I was mentioning a while ago. So in this setting, we have that basically psi is modeling the forest. So the location of each tree is xj, and to each tree, there is assigned an observable variable sj that indicates how visible each tree is. And we have observations that recall some partial surveys of the forest. And we tested this model on a real data set of Norwegian spruces. Well, actually, this data set already contains all the information about the data set about the trees. So we were actually doing the thinning, generating observation by hand, assigning to each tree independent beta random variables for their visibility score, and then sampling Z1 to Zn. And we compare an oracle method where we use the full data set to fit the parameters of a Gaussian DPP, and we know the parameters of the beta distribution with an empirical Bayesian method where we use the marginal log likelihood to estimate all the parameters in the model. And as far as the estimation of the number of trees is concerned, well, the oracle method always gives basically the correct estimation. Well, here I'm showing the posterior distribution of the total number of trees for different sample sizes. And we can see that under the oracle method, what happens is just that the variance of this posterior shrinks as the sample size increases. But also in the empirical base, things are looking pretty good. If we have only 5 observations, which is arguably not a lot, then our estimates are slightly biased. But as soon as we get 15 observations, then we are pretty accurately recovering the true number of trees. In addition to recovering the number of trees, we can also visually inspect or provide a visual estimation of where are the missing trees by plotting the posterior probability that a tree appears in a given location dx. And here I'm displaying this posterior probability up to a normalization factor, and red crosses are the missing trees. And we can see that these basically they are all in the regions of highest posterior probability. So in conclusion, I hope that I've motivated that feature allocation models are useful in several applications in very different domains, and that studying this predictive characterization provides a principled way to choose a prior distribution. Moreover, we have also talked about these extended feature models, which offer many new possibilities for Bayesian modeling of feature allocations, such as further applications. The ones in spatial statistics is just the beginning, but also opens the door to algorithmic developments for posterior inference. Let me just touch on a quick comment about the predictive characterization for those priors inducing predictions depending on the sample size and the number of distinct features. So this is the case of what we call a mixed Poisson complete random measure. That is, mu given theta is a complete random measure, and theta is a positive random variable. But of course, this can also be interpreted as a Bayesian hierarchical model, where theta is the total mass of the Levy intensity, and we put a prior on it since we don't know it. And this shows that being fully Bayesian yields a predictive distribution. It yields richer predictive distribution on top of being robust. And indeed, this is not what is typically done in feature models, where empirical Bayesian methods are used to select hyperparameters. So this should argue in favor of being fully Bayesian. And having established this insight, then we can it is clear that we can obtain richer predictive distribution the more parameters we assume random in the expression of this Levy intensity. For instance, if we assume a 3-parameter beta process and we put a prior also on the tail parameter alpha, then we have predictions that depend on the whole frequency spectrum with a marginal increase in the computational cost. The other thing that I want to mention is the possibility of pinning down specific processes. So in the case of species sampling models, people before us were able to pin down the Dirichlet process, the Pitt-Major process, the symmetric Dirichlet distribution, while we were able only to pin down the class of completely random measure, which is pretty big, and the class of mixed Poisson and mixed binomial processes, which is much, much bigger. And so what happens is, what if we want to pin down specific processes? Can we start investigating also what happens on the probability of reobserving old features in order to aid in trimming down this characterization? Well, this turns out to be impossible. And in particular, in the class of completely random measures, the probability of reobserving an already seen features depends already only on how many times that feature was seen. And the distribution of seeing something new depends only on the sample size. And difference lies in the power law growth of certain statistics of the sample. So it is unlikely that we will be able to pin down specific processes by investigating this kind of sufficient statistics of the predictive distribution. So I think this is all. Thank you for listening, and I'd be glad to take any questions.
Thank you, Mario, for the great talk. And we have about 10 minutes for the questions. If you have questions, please raise your hand and I'll call your name. Any questions from audience? Okay, so then I have a very the small question. So like the later, like you proposed like a different distributions, I mean like a different processes and so on. Like have you looked at like their empirical performance, like how the difference and which one?
Okay. Oh, sorry. So you mean like this example?
Yeah.
Or
I mean like this.
Of course, one could model this as any feature model, and assume that these trees are i.i.d in the space. So the first thing that wouldn't be able to do if we assume a standard feature model is to produce this kind of plot, because this will be like all uniform probability in the space. I think that we have not looked at the empirical performance on the estimation of the number of trees. I suspect that if you don't really characterize the dependence or the repulsiveness across the trees, then it's likely that you will overestimate the number of trees. But we generated these plots like a few days ago, so it's still work in progress on this example. But thank you for the question.
Okay. Okay. Thanks. Any other questions? Oh, yeah. Okay. So then.
Hello, is Rafael here? Can you hear me?
Oh, yeah. Rafael, like, go ahead.
Yeah. Hello. Hi, Mario. I have just a curiosity. So you have this posterior characterization of the feature allocation model, right? So that is quite general.
Yeah.
So I remember there is work by Tamara Broderick and co-author discussing about conjugacy in future model. So do you have a kind of conjugacy result you do when you assume repulsion or attractiveness, you lose conjugacy? It's just a curiosity.
Yeah, I think that we lose everything basically. I think that even in the case, so they have conjugacy if they assume completely random measure, if I'm not mistaken. I think that as soon as you step out the class of completely random measure, then you lose any hope of conjugacy. So also in the case of mixed Poisson or mixed binomial processes, you don't get conjugacy. I mean, what you get is that mu prime possibly belongs to the same class of priors that you were assuming, but the whole posterior is not again an independently or a mixed Poisson process or a mixed binomial process. While they say, well, they have conjugacy, meaning that the distribution of mu and not of mu prime is again a completely random measure, where these are the fixed atoms of the completely random measures.
Yeah. And for the computational point of view, this is not a problem for you, right? If I got well. Or it's relatively...
Well, in general, we cannot really say what happens in general. So in this example, we were able to do some further calculations by hand, and basically we obtain a rather convenient expression for this posterior distribution. It's not straightforward because it's basically a Poisson binomial distribution, which means it's the sum of Bernoulli distributions with different parameters, and evaluating the distribution of a Poisson binomial is not straightforward, but we can do it. But in general, I would say that it's very difficult to do computations.
I imagine. Thank you.
Okay. Is there any other question? Okay, so then let's thank our speaker again, and I hope to see you all in next webinar. Thank you, Mario, and
thank you. Bye.
Everyone attending.